Sequences are fun. So we will learn about sequences in this video. And you have encountered sequences, I'm sure, when you tried these IQ tests, which you can find everywhere on the internet. So in many of these IQ tests, right, you have like a sequence of numbers, and then you need to try to find the next number. So for example, 2, 8, 14, 20. If you look a little bit closer, you see the increment is 6 between those numbers, so the next number is 26. Here, 1/2, 1/3, 1/4, 1/5, so the next number is 1/6. And then 3/4, 4/8, 5/16. So you might need a few more seconds actually to look at it. So the numerator is 6, and the denominator is 4, times 2 is 8, times 2 is 16, times 2 is 32. So in mathematics, sequences is just a formalization, a formal definition of these kind of sequences of numbers. So how can we find rules for these sequences? How can we generate sequences? And what properties do they have? So here's a definition. So a sequence is just an infinite list of numbers which we denote as A1, A2, A3, A4, or equivalently as A0, A1, A2, A3. You will see in the examples, which I do in a second, that sometimes it's just more convenient to start with A1. Sometimes it's more convenient to start with A0. Both is possible, and you just use whatever is easier. So let's look at these three examples. So I write an to be n plus 2 divided by n. Now, obviously here I cannot start with n is 0, otherwise I would divide by 0. So I start with a1. So a1 here is 3, right? So it is 1 plus 2 divided by 1 is 3. So a2, 2 plus 2 divided by 2 is 2. a3 is 5 divided by 3. This is then just 5/3. a4 is 6 divided by 4, which is 3/2, etc. Let's look at the next one. Minus 1 to the power of n. So this is an exponential function in the index n. Here we can start with n is 0. So we have a0 minus 1/2 to the 0 is always equal to 1. a1 is minus 1/2. a2 is minus 1/2 squared. So then the minus sign disappears. We get 1/2 squared, which is a quarter. a3 is then minus 1/2 to the power of 3. So we get minus times minus times minus, which is minus. So we have minus 1, and then 2 times 2 times 2 is 8, minus 1, 8, etc. The last one, again we can start with a0. So if n is 0, we have 5 to the 0, which is equal to 1, plus 1 is 2. And then the next element is 5 plus 2, which is 1. a2 is 5 squared plus 1, which is 26. a3 is 5 cubed plus 1, which is 126, etc. So that's very simple to create these sequences. But what is nice, we can now visualize them similar as we visualized functions. We can have a graph of n and the value an, and then I'll show you what we get. So here I plot n versus an for these examples from before. Here I give you the numbers again, and then in this view graph I just plot these numbers. So the first element was 3, and actually we started at 1. Okay, so here's 1. We had no 0 element. Then we get to 2, then we have 5/3, then we have 3/2, etc. And I plotted the first 15 numbers. And you see they kind of line up very nicely. You could almost kind of plot a curve through here. It seems like they all live on the same curve, but I don't do this just yet, so we can maybe talk about that later. Also, it seems like if I use larger and larger numbers, so maybe like 15,782, I might actually be somewhere here, right? So maybe somewhere close to 1 or so. So here's the graph for the second example. A equals minus 1/2 to the power of n. So here are the elements again. The first entry is 1, which is right here. The next one is minus 1/2, which is here. And then it comes 1/4. Then comes minus 1, 8, etc. And you see this sequence, so it jumps from positive to negative to positive to negative, which is called an alternating sequence or also an oscillating sequence. Again, we will discuss these properties in much more detail later. Here is just one example where you can see that such an alternation in the sequence can happen. The third graph is this one. So the first numbers 2, 6, 26 and 126, they're all here. Okay, and they're so small that you can't see them because look at the scale. So the 15th entry is at the order 3 times 10 to the 10. So this sequence gets really, really huge, and the values will kind of diverge to infinity. They become bigger and bigger the further on you go. Okay. Let's do it the other way. So if I give you a sequence, how can you come up with the formula? So let's look at the numerator for the sequence. So numerator is easy, right? You have 3, 4, 5, so the next one would be 6. But now we want to associate this with the element A1, and this is the element A2, and this is the element A3. So then I write 3 is 1 plus 2, and 4, the next element, is 2 plus 2, and the next element again is 5 is equal to 3 plus 2, and so here are the pointers. This is the 1, this is the 2, and this is the 3. So then it leads us to the general formula for the numerator, which is n plus 2. For the denominator, we have 4, which is 2 to the 1 plus 1. 8 is 2 to the 2 plus 1. 16 is 2 to the 3 plus 1. So then we get, for the denominator, 2 to the n plus 1. So then in total, this sequence can be written as an is equal to n plus 2 divided by 2 to the n plus 1. So that's also quite kind of straightforward. Another way to define sequences is by recursion, or called recursive. So if in a recursive sequence, the next element, an plus 1, depends on the previous numbers, an minus 1, maybe even more. A recursive sequence is also called a difference equation. This is here. And you can write this that an plus 1 is a function of all the previous elements. In the simplest case, an plus 1 is just a function of an, and this is called a difference equation of first order. And they are most important. In this case, f is called the updating function or the map. So let me give you two examples, one for a first order difference equation and one for a second order difference equation. So a first order difference equation arises in population growth, for example. So if you have individuals like viruses and they reproduce, and let's say they produce 40 new viruses every day. Okay? So then the next day, an plus 1 would just be 40 times whatever virus load you had the day before, 40 times an. So let's start with one virus. So let's say A0 is 1, and then A1 is 40 after 1 day. After 2 days, we have 40 times 40, right, which is 1600, and so on. So then you can figure out that after n days, you have 40 times 40 times 40, and this n times. So you have 40 to the n, which is a big number if n is really, really big. Another example is the famous Fibonacci sequence. Fibonacci divides the sequence to describe the growth of bunny populations. So you start with one mother and one father, and if they reproduce, they get one daughter. The next element is just one more than we had before. To describe it in general form, he devised the formula that fn plus 1 is equal to fn plus fn minus 1. So you take the previous two numbers and add them up and get the next number. So let's do this. So then the third element would be the sum of f1 and f2. 1 plus 1 is 2. The next element, f4, is f2 plus f3. Okay, so that is then 2 plus 1, which is 3. The next number is the two previous number added, so 2 plus 3 is 5. f6 is then again the addition of the two previous numbers, which is 5 plus 3 is 8, etc. So this formula has been used a lot in mathematics. It has to do with the golden ratio. I don't know, maybe in class we can discuss what the golden ratio is all about. But the original motivation was to understand the growth of bunny populations in a park. So let me summarize. So we found actually two ways how to define sequences. One is an explicit way, where we write down an is something with n and n squared and e to the n or whatever. And we have a recursive way, where we define an by previous elements an minus 1, an minus 2. Now we also found that they have very interesting behavior. And the few one we have seen here, there might be more. So if I plot n, in the one example, we kind of seem to converge to a common number. And this is what we call convergence. And we will learn in later videos and in class what convergence really means. We had another sequence which did the opposite, right? It started somewhere, but then became really, really big and did not seem to converge. And this is what we call divergence. And then we had another sequence which would jump around the x-axis. So it would oscillate, this is called oscillation, or in this case even alternate between plus or minus. And there might be more behaviors of sequences. So later we will study sequence in more detail and try to understand what is convergence, what is divergence, what is oscillation and alternation. But wait, let me introduce two of my best friends, Tollo and Marlow. So here are Tollo and Marlow, and they are from the species of Hylodrillosaurus. Now, Tollo and Marlow will tell us a little bit about how they feel about calculus. And so let's ask Marlow. Marlow, what do you think was an important message out of this video on sequences? Sure, of course. Yeah, I certainly agree, but maybe that was not the message of this video. So we try this again in one of the later videos.